Hey, good morning, everyone. I hope you are doing all right. And next class, I hope you know this. Next class is final. And the format going to be similar to midterms, but it is going to be cumulative. Cumulative. I don't know how to spell it. I'm sure that is wrong. I guess there is 2M somewhere here. So again, you have seen all these materials. Most slides, you have seen them. So that's why it's a review. But remember, to do well in the final, I strongly suggest you do all the worksheets. See if you can do them and understand. Better start with a blank sheet that I have posted, right? Blank, without feedback or anything like that. See if you can do that. If you can do all the worksheets with just the formula sheet, then you will do very well in the final. That I can guarantee. But if you just read the feedback, then of course, you may know some of them, you may not know some of them, so you may not do very well. And start with the worksheet and go through all the clicker questions we have done in the class. And after that, look at the problems we have done in the class. Those three things, okay? So now getting back to the basic, we started semester with the kinematics. Kinematics includes graph and the equations, right? So we started defining position. And in a graph, how do you find position? If it is position versus time graph, you simply read the graph, okay? And a displacement between 2 points always, okay? So if we have 1 point and another point, then this being initial and this being final, you draw displacement starting from initial position to the final position. So that is a displacement vector. It is a line with arrow. So it starts from initial to final. But if you are finding same thing from the graph, then what do? You read the 2 points, right? You mark 2 points. For example, let's say if we want, let's say if we are looking at these 2 positions, then what happens? You read its value or positions and find the difference. So that is the displacement from the graph, okay? So again, I'm talking about position versus time graph. But from velocity versus time graph, for example, if we have that, then it's going to be area under. So displacement is area under velocity versus time graph. From the position versus time graph, how do you find it? You just read 2 positions and find the difference. So it is like a rise, okay? Now, if you are finding average velocity from a graph, what do? You find the displacement between 2 points, just like we just talked, and divide that by the time interval here, Okay, so time interval. So it's like a rise over run. So that is average velocity. And there can be instantaneous velocity rather than giving you 2 points, 2 times. You may be asked, okay, what is the speed or velocity at a particular point, particular time? That is instantaneous. So to find that from the graph, put a point on the graph and right next to it, put another point and draw a tangent line. So slope of this tangent is instantaneous velocity. And if the slope is changing, that means object is accelerating. If slope is fixed, like if you have a straight line, then constant velocity means it's not accelerating. Okay, so this is position versus time graph. So for a velocity versus time graph, slope is acceleration. So first, whenever you see graph, you need to look at what graph it is. Position versus time graph or velocity versus time graph. Mostly we're going to be talking, we have talked about those two graphs. Okay. And that's how you go about it. Learn how to find position, how to find displacement, how to find average velocity, how to find instantaneous velocity, and also learn to see if it is accelerating or not from the position versus time graph. And similarly, learn what the area under velocity versus time graph means and what the slope of velocity versus time graph means. Okay, so mostly velocity versus time graph, we'll be talking about constant slope graph. Constant slope means acceleration is constant for velocity versus time graph. Kinematics, they are all about constant acceleration. Okay, so with that said, now let's look at this question here. So you have a minute and 30 seconds. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly we got everything. So let's look at one by one. Okay, so let's see what went wrong, if something did wrong for you. Okay, so magnitude of the acceleration of car C is greater than the acceleration of car D. So this is position versus time graph. How do you know about acceleration from position versus time graph? So if slope is changing, then it is accelerating. Slope constant means A is 0. Slope constant, A is 0. So in both cases, acceleration is 0. Yeah, their velocity is different, slope is different, okay? But both of them have 0 acceleration because slope is constant means velocity not changing, okay? So that's why the acceleration is same for both, okay? A is 0 means A is same for both. So that's why A is not correct. And so is the B, okay? So if you chose, A is correct answer, you are thinking uh, the velocity, not acceleration. Slope bigger for C means velocity is larger, not the acceleration, okay? And now at t is equal to 10 seconds, both cars have the same velocity. So do they have same slope at that point? They have different slope. See, what is same is position, not the velocity. So what that means different velocity. Different V. Okay. Both cars have the same acceleration. Oh yeah, because both of them have 0 acceleration, so same acceleration. Okay. Both cars comes to the rest after 10 seconds. See, they are still moving, so this is not correct. So D is correct answer in this case, folks. So many of you chose they have same velocity at 10 seconds. So what went wrong? They don't have same slope at that point. So how do you find slope? You need to draw a tangent line. So tangent line is a straight line itself for a straight line, okay? So they have two different slopes. They are not same slope. Okay, so velocity is slope. Don't forget, okay? So slope increasing, slope 0, slope decreasing. You see that? So negative slope. Oh, it is negative slope, I should say, rather than decreasing here. Negative velocity. Zero velocity. So less slope, less steeper means less velocity. So over here, slope is down, sloping down, negative velocity. But if this was going something like this, positive velocity, even on the negative side, okay? So that's how these graphs work, okay? So, oh, there is a velocity graph. Let's quickly pull on that one as well. A minute for you. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, now let's see what we got. So we got all of them, but a little bit more for B. So let's see, it's talking about speed. Slowing down means also speed. Velocity is speed. And this is velocity graph. So simply read the graph to find about speed and velocity from ET graph. So here at the beginning, t is equal to 0, right? The velocity is 0 and t becomes more, means velocity is now larger. So remember, negative means direction. For the vectors. So velocity is increasing, speed is increasing means it's speeding up. So it is A is the correct answer, not B. It's going in negative direction does not mean it's slowing down, okay? The value is increasing. Slowing down graph would look something like this. From larger value coming towards the smaller value. Slowing down graph would look something like this, okay? From larger value towards the smaller value. Remember, this is 0, 0 point. So time is increasing this way, velocity is increasing this way and that way, both way. Negative sign simply means direction. So for the vector, that's so velocity being vector, we need to keep that in mind. Okay, so now, so from after graph, that's kinematic equation. So how do we read this? Final velocity of an object is equal to initial velocity plus acceleration times time interval. You need to read something like that, okay? And if you are using this equation in horizontal direction, you write something like this. And if you are using this in vertical direction, replace x by y, okay? It could be in x direction or y direction. And same thing goes here. This is displacement. And you know displacement means final minus initial, okay? So these two equations have time on them. This one doesn't have time. So if you don't know time and if you are not trying to find time, you use this equation. But if time is given and you are trying to find time, then consider using one of those. Now, should I use this one or that one? See, you can use this first one to find the final velocity, or if the final velocity is given. But in this case, there is no final velocity. So if displacement distance is talking about, this is the way to go. Displacement distance with time, this is the way to go. Displacement without time is this equation to go. This equation basically came from these two equation, combination of those two equations. Okay. So here is a question. So I'm writing these along the x direction, but of course you can use that in y direction simply by replacing x by y. So here is a question and you have 2 minutes to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. So mostly B and D, double or 4 times. So this question says dropped, means initial velocity is 0. So this is talking about vertical direction. So maybe we should write that. And we know AY is G downward always. Okay, so those two things we know, and it's asking for distance or displacement with time. So displacement and time are related through this equation. So this is the equation to use. So now what do we know? BIY is 0. So this goes 0. So displacement or distance is now half gt square. So we can say, okay, down is positive. So that way we don't have to worry. See, it's going down, so displacement is negative. G is also negative if you choose up as a positive. But if you choose down as a positive, delta y is positive now, and acceleration is also positive. So this is your equation. So this is constant, this is constant. So that means displacement simply depends on time. So for t, this is simply d is half gt square, right? Now, if you double the time, so when t goes to 2 times t, then t square goes to what? 2t has to be squared. So that means it becomes 4t squared. So it picks a factor of 4 extra. So this half being constant is not changing, it remains same, g remains same, only t is changing. So when you double t, t square becomes 4 times larger, means displacement also becomes 4 times larger. So that's why D is the correct answer for this. So this is not linear in T. See, distance is not linear in T. If there were just T, then 2D would be correct answer. Okay. Okay, so graphs and kinematic equation. And after that, laws of motion or dynamics, right? So laws of motion, we talk in terms of net force, not just force, rather net force. So there are two forces here, but net force here is 0. See, the length same. So if this is F, and if we say this is positive, then this is going to be negative F. So when you add them, what happens? Net becomes 0. Okay, so think in terms of net force, not just a force, unless there is only one force that's acting, okay? So we have learned about these different kind of forces and how to draw them, okay? And of course, we also learn about buoyant force. So if something is in a fluid, then it experiences upward force, that's called buoyant force, right? So in addition to these forces, we have learned about buoyant force. So now, Newton's first law. So when net force, this net force is 0, then object gonna be moving with constant velocity, and constant includes 0. So if object is not already moving, it's not gonna start moving because of the net force 0. If already moving, then it will just keep moving without slowing down, okay, with constant velocity. So often what we think is if we stop applying force, object slows down. That's not true. As long as net force is 0, object keeps moving with constant velocity. So that's Newton's first law. So for example, the spark keeps moving with almost constant velocity in this case because there is friction. So the friction slows down a little bit. So whenever we see something slowing down, that means net force is not 0. Some force is making it slow down. There is some net force acting on the object opposite to the direction of motion, okay? So when it's slowing down or speeding up, we call object is accelerating. So when object is accelerating, then we use this equation something like this, right? So when the acceleration is 0, then this right-hand side becomes 0. So that's how we use Newton's second law. And how about third law? Action and reaction equal and opposite. So if you getting tossed by something, you are also touching that object and applying same amount of the force the object is applying to you, okay? So if somebody pushes me in my head, I'm pushing that person back with my head with the same amount of force in opposite direction, okay? So that's what this Newton's third law is about, okay? So here is a question related to Newton's laws. So what do you think? 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly C. So the car adjusts the same amount of force on the truck adjusts on the car. So yes, so they are action-reaction forces, okay? So when we talk about force between two objects, one to another one and the other one to first one, that force is, that pair of force are action-reaction force, and that means they are equal, okay? So you may be wondering why it is speeding up then, right? So remember, it is about net force on the truck. So net force on the truck could be force from the car. So as long as there is net force on the truck, so if I make free body diagram of truck, see there is this, and there can be some friction force, let's say, and force from the car here, right? Force on the truck. So as long as these two forces, net force, the Fc is bigger than Fk, it's going to accelerate, okay? So that's why it is accelerating. Car is applying larger than friction force. That's it. That's all you need. So for example, let's say a car gets hit by a truck. We think, okay, the car is getting a lot of force from the truck. Whatever that force is, car is also exerting with the same amount of force on the truck. Okay, action and reaction, remember. Okay, as long as forces are action and reaction, they must be same. So this is about Newton's third law. So now here is another question, and you have a 1 minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. Mostly A and B. So it says constant velocity. Constant velocity means net force is 0. Okay, so that's why B is correct answer. That's Newton's first law. So if there was force, net force, towards the right with constant strength, then this would be accelerating. See, net force m times a. So net constant force means constant acceleration. Constant acceleration means velocity is changing with constant rate. So make sure to understand the difference between velocity and acceleration. Okay. Constant velocity means velocity not changing. Constant acceleration means velocity changing at constant rate. So like it's going from 2 to 4 to 6 to 8. See, the difference is 2 always. 4 to 6 to 8. See the difference? 4 to 6, what's the difference? 2. 6 to 8, what's the difference? 2. So as long as those differences are equal for equal time interval, velocity is changing at constant rate. So that means it's a constant acceleration. Okay. So now here is another question. And you have a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here. So we did not get D, but we got everything. So in this case, it is accelerating and moving to the right, same direction. Accelerating means velocity is changing. And when velocity and acceleration are in same direction, that means velocity is increasing. Okay. So V A, no matter how big or small the acceleration is, as long as they are in same direction, B is increasing. But when acceleration becomes opposite, so in this case, acceleration decreased. That does not mean acceleration reversed. No, still in same direction. So for example, let's say if it was accelerating 4 at the rate of 4 at the beginning, later, let's say it started accelerating at the rate of 2. What that means? So now, if the velocity was going something like, let's say 0, 4, 8, see the change is 4 means it increases by 4, right? 12, so on. Now after that, rather than going 16, it is going just 14 because now it's accelerating slower rate. So that means it becomes 14. So it still increased from 12 to 14. Okay. So it's still increasing. rate of increase slowed down. That's what the acceleration decreased means, okay? So the correct answer would be C in this case. Unless the direction of acceleration, reverse, the velocity does not decrease, okay? If we did not know they were moving in same direction, if the acceleration was in same direction, if we did not know that, then both of these are possible answer. So in that case, you would have been correct. If we did not know what direction the acceleration was or what direction the velocity was. But here we know acceleration and velocity are in same direction. That means it's increasing, okay? So now to use Newton's law, we need to write things in terms of components, right? So here is one such example. There is an object and a force named as a P rather than F is being applied here, okay? But it acts in a particular angle, right? So this is horizontal line. So this is also horizontal line. The box remains rest. So there is it says there is some sort of friction on the box, and now is talking about normal force on the box due to the floor. Okay, so for this, replace object by a dot, draw a free body diagram, and break the force in horizontal and vertical direction, because if it were to move, it would move in flat surface, means in horizontal direction. So that's why you want to choose one axis in horizontal direction in this case. Although force is inclined, the object is sitting on horizontal surface. If it were to move, it would simply move in horizontal direction. So that's the one axis you want to choose, okay? So choose, let's say, one axis in horizontal direction, another axis in vertical direction, draw forces, and find component of the force that's neither in horizontal and vertical direction. And after that, use the equation here, using this condition that box remains at rest. So those are the things you should be doing. So go ahead, you have 2.5 minutes for this. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. So mostly D, and there are quite a few C as well. So both P sine theta. So W is in that direction, and P is acting in that direction. So this angle is known, means this angle. So this is the angle made by P with the horizontal. So it's like this angle is known. Okay. So that means normal force is here, and friction force, let's see, is getting kind of pushed this way, means friction gonna be in that direction. Oops, in this direction, right? So there would be friction force, and since it hasn't started moving, the friction force would be static friction force. So this component would be cosine component, because this theta is, this component is adjacent to the angle theta. So it would be P cosine theta, and another one would be acting here, so P sine theta. So now, since we are looking for normal force, we can write equation in vertical direction. Okay. So sum of forces. So let's say this is positive y is 0 in this case, because it is at rest. So velocity is 0, acceleration is also 0. So normal force up means positive, W is negative, and P sine theta is also negative. That is equal to 0, means N is now W other side positive, and P sine theta is also positive, looks like. Both of these negative becomes positive when they are pushed to the other side. So looks like D is the correct answer in this case. And if you are wondering, what if I choose down as a positive y, will the answer be same? It should. Choice of coordinates shouldn't change the answer. So if that's the case, the n would be negative and these two would be positive. So if you move n to the other side, now you see n gonna be still sum of those two. Okay, either way, the same answer as it should be. Choice of coordinates should not change the final answer. Okay, so that is kinematics and dynamics. So I think it's a good time to take break. So let's take break, and then we're gonna move to the work and energy from here. Okay, I'll see you in 5 minutes. Okay, folks, welcome back. So kinematics, dynamics, and after that comes the conservation principles. So before we do conservation principle, we need to learn some vocabularies, and because of that, we learn what work done means, what energy means, and then we talked about conservation of energy. So work done transfers the energy. So how do we define work done? Is the work done by a force is equal to the product, is equal to product of the force times displacement times the cosine of angle between force and displacement. Okay, it's not any angle. So to find work done, always draw F and D to figure out theta. Okay, no guess, just draw and figure out. Okay, and only values. Do not use negative or positive sign for F and D. That's why we are drawing F and D here, okay? To figure out theta. Okay, with that, let's do the polling. And you have total a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So mostly A, and then B and C. Nice staircase here. So here, work done by the force of your hand. So when you are lowering a book, it's like something, any object, when you are lowering this with constant velocity or not letting it free fall, you are applying force upward always. Okay. The force of your hand is upward. And displacement in this case is down. So theta here is 180 degree. So the work done by the hand is force from hand times displacement times cosine of angle between them, which is 180 degree. And cosine 180 degree is -1. Okay. So that means the work done in this case is negative, not positive. In this case, work done by gravity would be positive because gravitational force is acting down and object is also moving down. So the angle between them is 0 degree. So that's how you find the work done by any force. Okay. So that's what you need to do. And if there are multiple forces acting and you want to find net work done, then you can find work done by each of the forces individually by drawing FD diagram for each of the forces and then add them together. Okay, so that's going to be net work done. Or you can first find net force in the direction of displacement and find the work done by net force. Okay, and we learned that work done by net force is equal to change in kinetic energy. Means oh, There has to be squared. Okay. So after learning about work done, we also learned that work done by gravitational force changes the potential energy of the object. And the potential energy, we denoted gravitational potential energy by mgy. Okay. So final mgyf, where fy position need reference to determine what the position of the object is. Position from where, right? So we need to keep that in mind. So now with that said, let's talk about conservation of energy. Okay. So when there is no friction or when friction is negligible, then total energy after, I mean, yes, even when the friction is, this equation is valid, total energy after and total energy before. But if there is no friction, so when we say energy, energy could be sum of kinetic energy, potential energy, and thermal energy. So this thermal energy comes from work done by friction or non-conservative force. But if the friction is negligible, so in this case, there is no information about friction, okay? So when you are in a skateboard, it's a kind of rolling. So there are small wheels that rolls. So because of that, friction can be negligible, okay? So that's what we are assuming here. So in this case, says compressed at a distance of that much shown, the spring constant of the spring, so K is 6,400 Newton over meter, and the mass is 50 kilogram, and it's asking us speed of this skateboarder on the horizontal ramp. So its final position is somewhere along the horizontal, not over here, okay, but just here. And both, both of these we did in worksheet, and I think we also did in class. Just in case what we do here is not enough for you, you can look at this work energy worksheet, okay? So this is going to be our final, and this is going to be initial, okay, for the skateboarder. But for the spring, xi gonna be equal to x because it says it's compressed a distance x, right? So that xi is x is 0.50 meters. So initial position of the spring, it's already compressed, okay? And the final position of the spring, once it pushes the skateboarder, it is now relaxed, right? So it's not compressed anymore. So xf becomes 0, okay? So that is the final position of the spring, but the final position of the spring border is here. So to find the final position and initial position of the spring border, we need a reference. So let's choose this line as the reference line. So that means initial position is 0, where the position at reference line is 0. That's the meaning of reference line. It's still on the reference line means YF is also 0. But if we were talking about this, then YF would be equal to H, okay? But we're not talking about this portion. And VI is 0 because it gets pushed from by the compressed spring, okay? It says it's launched. So that means at the beginning it wasn't moving, the skateboarder wasn't moving, right? So we want final velocity, okay? So when you have position, velocities, and so on, that means it's a good problem for applying conservation of energy, okay? So since friction is negligible, so whenever friction is negligible, we can use final kinetic energy plus final potential energy is equal to initial kinetic energy plus initial potential energy. So this is half mBf squared, final kinetic energy. How about final potential energy? There are two possible potential energies. One is gravitational potential energy. Another one is elastic potential energy. So that's why both of these are okay. That is the final side. And for the initial side, you do the same thing. You repeat this, okay? So since I need a room, I'm gonna erase this here and write it. Half mvi squared plus mgyi plus half kxi squared. Okay, so a lot of things are 0 here. And by the way, since height is not changing, you can say both of these going to be 0. So even if you don't include that, you will be fine. But here we are doing review, so I am writing everything, right? And if it was a rolling object, there would be another kinetic energy, half I omega square, remember. Here, little wheel is rolling, so its mass is negligible compared to the whole mass of the person. So we are neglecting it. So I'm going to get rid of that because we need room here. So a lot of things are 0. Just like I said, position height is not changing. So we chose reference point right there. So that is 0. But if you are doing over here for this point at maximum height, then you need to include this positions as well. Okay. So now regarding x, xf is 0. So that means 0. And initial speed is 0. So that means this is also 0. So what it is saying is initially it has only the elastic potential energy because of the compressed spring. And finally, it has just the kinetic energy. It's moving, okay? Spring does not have energy anymore. Finally, we are left with just this. So half cancels. So we are looking for BF. So that means it's going to be k over mxi squared. Oh, this bf, but they said there is bf squared, so I need a square root. And if you want to write nicely, you can do this, because xi is squared means when you take the square root of that, it's going to come outside. So you can write this side or this side here, xi doesn't matter, okay? So that's how you solve this kind of problem. So this is how you use conservation of energy, okay? So you know these numbers means needed, you can find the speed. Okay, so that is using conservation of energy. And then we also talked about power, which is rate of change of energy, right? Where change in energy could come from change in kinetic energy and change in potential energy. Sometimes both energy may be involved, but most of the time either is kinetic energy changing. For example, if a car or object is speeding up in a flat surface, then only kinetic energy is changing. But if something is just falling up and down, so in that case, only potential energy is changing, right? So you can think of something like that. Okay, so that is energy, power. And then after that, we started talking about momentum. So momentum is product of mass times velocity. And then another thing we learn in this is impulse. Impulse is product of average force times time interval, and it is area under FT graph as well. If you have force time graph, then how do you find the impulse? Just find the area under, okay? So this thing is talking about impulse, and it is change in momentum. So we learned that impulse is also equal to change in momentum, and we derived this equation by using Newton's second law, okay? Impulse, momentum theorem, okay? So to find impulse or change in momentum, you can find impulse or change in momentum. Here, this is moving something like this. So this is initial momentum. And once it goes something like that, is that. So there is no numbers or the values of the momentums are given. So if you are looking for change in momentum, you need to use this PF minus PI and draw using tail step number 1, tail 2, tail. Step number 2, from tip of initial change. So it's true for momentum, true for velocity. And remember, change in velocity, direction of change in velocity is same as acceleration. So we use that a lot to find direction of acceleration. So with all these, now I'll open the poll and let you poll on this. Go ahead, draw using these two steps and find the answer and poll. You have total a minute to answer this question. Oh, forgot to warn. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. So mostly A, that says straight up. So how do I do that? So let's say PI is there, something like this. PF is going something like this. So if I were to bring the tail over there and draw tails together, this is going to be PF. So this is step 1. Step 2, from tip of initial to tip of final. So that gives me delta P, which is step 2. Okay, so it's up. Yes, so it is straight up. So after learning about momentum, impulse, and so on, we talked about conservation of momentum. So it's like a conservation of energy. Total final momentum is equal to total initial momentum. We use this kind of situation when two objects are colliding. Okay, in collision situation, we use conservation of momentum. So for example, when we fire a bullet on a block, you can use conservation of momentum, okay, to find with what speed the block and bullet are going to start moving and so on, right? So momentum, so since it's a collision, usually we're going to have two objects involved. So because of that, you write final momentum of object number 1. Momentum means mass times velocity of object 1 plus mass times final velocity of object number 2. So that's the total final momentum. Okay, that is equal to, and you repeat that to the other side by replacing final by initial. And you write velocities with sign because vector velocity is vector. Okay. So usually mass and velocities, some of the masses and velocities are given, and you are asked to find another one, and so on. Sometimes you may have to combine conservation of momentum and conservation of energy together. So there is worksheet, momentum, collision and momentum worksheet over there. This problem is done, okay? You want to practice that. I did not bring a problem related to that. So I'm going to move to now fluid. Fluid static and fluid flow, okay? So two things we learned, okay? when, object is in fluid, we learn that there is buoyant force. And that buoyant force is given by this equation, where this is volume of fluid displaced. And always up, vertically up. When object is fully inside the fluid, volume of fluid displaced is same as volume of the object. Okay. So now here it's asking you to compare two forces. Okay. But before you do that, draw a free body diagram. And since this is in equilibrium, you can use sum of forces in vertical reduction as a 0. Okay. So here, go ahead, draw a free body diagram and look which option is correct. You have a minute and 30 seconds to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So in this case, we draw a free body diagram. Weight is vertically down. Here it's being held by tension. But we know since this is in a fluid, water, they're going to be buoyant force. So now these two forces are balancing mg. So to balance one force, you needed two forces. So that means this force must be larger than any one of these two forces. Okay, so mg is larger than tension. So C is correct answer in this case. You can do that even without writing equation. See, many of you chose T is equal to mg. That would be the case if there was no buoyant force. If buoyant force wasn't there, then that would be the case. But remember, when object is in a fluid, there is always a buoyant force. Okay? So now, if I were to write equation for this is going to look something like this. So let's say up is positive, y means T positive minus FB minus, sorry, not minus, but positive FB, and minus mg or negative mg is 0. So if I were to solve for T, it's going to be mg minus FB. So what do you see here is to make, mg equal to t, you need to subtract fb. So it's like saying 10 minus 2 is 8. So 8 so that is like saying t is smaller than mg. Okay, so that's how you use it. But let's say if this thing was accelerating, then, like let's say if the object is accelerating down or up, then you can use the same thing with the mass times acceleration in vertical direction. So you can use Newton's second law there. So after that, we talked about fluid flow. So one equation was, we said equation of continuity, okay, where this is area of the pipe where the fluid is flowing, okay, and this V is the speed of fluid. So if one increases, another one has to decrease. So that's why when let's say if we have a garden hose, and if you close part of the opening of the garden hose, you made area smaller. So when A becomes smaller, when A goes down, B has to go up to keep this thing constant. So that's why the water starts coming faster. So that is one equation of flow. Another equation is Bernoulli's equation. Okay. Here, this is Bernoulli equation. So in this case, this is pressure. Now we are including pressure, and pressure is kind of force, force related. So looks like there was a question that I missed. So without the string, FB would be equal to mz. So yes, if the tension wasn't there, so there would be FB and there is mg. So no string, no tension means they would be equal. That's right. Okay. So here, this is pressure. So pressure is like, just like for the rotational motion, we use torque instead of force. Similarly, for the fluid flow, what do? We do use pressure instead of force. And pressure is average force divided by area. And this is density. And this is, of course, the speed of both of these are for the fluid. And this is position. So it says the sum of these three things remains constant. Okay. So now I will pull on this question. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly B, but we got all of them. So paper above the, the air above the paper moves faster, so the pressure is higher. So larger speed means this term is larger, means the pressure has to be smaller, not larger, right? If one increases, another one has to decrease so that it remains constant. So looks like, yeah, so the air above the pressure moves faster, so the pressure is lower. So looks like B is correct answer in this case. So basically, it's basically talking same thing, okay? So because of that, what happens is that the paper strip rises. Let's say if I have something like this. Oh, see, rather than going down, it's coming up. Okay, so the object moves to a still lower pressure, right? And when we have two paper strips, something like that, and if I were to do this, I think we did this during the class, they come closer together when I blow in between the paper, rather than going far away from each other, okay? So looks like this is question from the oscillation. So it's like a pendulum, right? So where is the acceleration greatest? So it's going from, in one side A, it's D. So C is equilibrium. And B is somewhere in between equilibrium and maximum displacement, right? So it's asking us where the acceleration is largest when it is oscillating something like this, right? So what do you think? Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got. Mostly C, which is A and D. C is A and D. So that is a correct answer, because when it is there, there is maximum force. So for example, if I were to draw a free body diagram of a pendulum, mg is vertically down and there is tension here. And we can write the component of mg. One along the string. So when this angle is theta, this angle is also theta. So this side becomes now adjacent. So this is mg cosine theta. And mg sine theta is perpendicular to the string. So it's the mg sine theta, that force, so that force depends on mg sine theta. We call that force restoring force. So this negative sign simply means it is restoring. It acts in the opposite direction of displacement. Okay. So now what happens is mg sine theta. So m is not changing, g is not changing. What is changing? Theta is changing. That's why the force is changing. And what do we know about sine theta? Sine 0 is 0 and sine 90 degree is 1. Okay. So when angle is larger for sine, when angle is larger, its value is larger. So at these points, that's where the angle is. And we measure angle from this equilibrium point, okay? So that's when the angle is largest. So that's why this becomes largest. So largest force means largest acceleration. That is the systematic way of looking at it, okay? But it acts like a mass spring system. And we learn for the mass spring system, same thing goes for the acceleration or the force, right? And we also learned that the speed here going to be 0. And speed at equilibrium point is maximum. So anyway, so that is the property of oscillating pendulum or spring. So that's how it works. And we wrote equations to describe the motion, right? And we also made a graph how the position versus time graph of oscillatory motion looks like. Something like that, right? And the speed, or should I say velocity? Because slope of position versus time graph is a velocity. And positions, of course, we know positive positions on the upper side, negative positions on the lower side. And for simple harmonic motion, we know acceleration is, so x and a opposite sign. So in this region, x is negative, means acceleration is positive in this side. In this side, on the upper side, x is positive, so the acceleration is negative, and so on. So that's how we can use that information. So that's the kind of thing we learned in the oscillation. And then we also talked about energy and how to use conservation of energy concept. We just talked about that just last class, right? And here is question related to the energy. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got. So mostly A, and that is correct answer. So, oops. B is maximum at equilibrium point. Since K is half mv squared, wherever the velocity is maximum, kinetic energy gonna be maximum there, right? So I realized I did not bring question related to torque and rotational motion. So please look at the worksheet of that one carefully, right? Learn how to find torque. There are 3 different ways you can find the torque, right? So torque definition is RF sine theta. So here, angle between R and F, okay? Or you can write torque as RF perpendicular. So if you know perpendicular component, if you can find perpendicular component of force with respect to R, then that is right. Or torque is lever arm times force. Lever arm, learn how to draw lever arm using 3 steps. So it looks like there is a question on the chat that says review question will be posted for the final exam. So these are the reviews. This slide is posted on the Canvas where it says class slides, right? And review questions are the worksheets, and the clicker questions we have done throughout the semester. They are not going to be specific review question, okay? Here I have tried to review the main idea, So go back, start with the blank worksheet and work on them if you want question to work on for the review, okay? So I'll leave you here, folks. I'll see you next class. Make sure to you sign into the Zoom using SSO option. How to do that, I posted that, during the second, somewhere during the second work midterm. Maybe I'll also post again. Okay. So I'll see you folks next class for the final. Okay. Prepare hard.